Namaste everyone. Welcome to Wave Optics class. Already we have seen many ideas of waves. In the previous class we have seen the different phases of different particles in a particular wave. And if two particles are situated at a particular distance in terms of lambda and how they are differing by phase. For example, if two particles are separated by a distance of 1 lambda, what is the phase difference between those two particles? And how will be the particle in a particular phase, and what is that condition of the particle, and how will be the phase, or how will phase affect the superposition, what will be the resultant wave. We will recap all those things very quickly, and today I hope you will understand what is interference very properly. That is what I hope. Let us see what happens at the end of this session. So shall we move on? We will recap few things, whatever we have studied in the previous class, and then we will move on to the next important, that is superposition. Okay, so yesterday we have seen this, how particles vibrate at different positions as the wave propagates. So if one particle is disturbed, others will also get disturbed because of the force of cohesion between the different molecules in a water. For example, in water, different water molecules are attached together by a cohesive force, and that makes the different particles get disturbed if one of the particle is disturbed. But all of them don't vibrate in same phase, and if one particle goes to the top and other one will be at the trough, and when one is at the crest, another will be at the mean position, so there will be different phase. As if we have some people in this world who are in the phase of their say job, and some of them are in the phase of retired life, some of them are in the phase of education, some of them are just born. So there is a phase difference between each and every person in this universe, and that phase difference will be maintained throughout their life. What the age difference you and your mother have will be continued throughout the life, and if you are having age difference of 25 years, that 25 years will be carried throughout. Similarly here, that phase difference will be carried throughout. Okay, so we say that this distance is lambda. Any two particles at a distance of lambda will be always are in phase. Of course, they will have a vibration difference of 1. If this completes 10 oscillation, this will be completing 9th oscillation, that's all. And these two have a path difference of lambda by 2. And you know how to connect all these path difference and phase difference. Now, phase difference is equal to 2 pi by lambda into path difference. You know that formula, of course. And here, if you take any two particles, for example, so this is the formula, phase difference equal to 2 pi by lambda into path difference. Now, for example, if you take two particles separated by a distance of lambda, lambda by 2, they should have a phase difference of pi. That means they are vibrating in opposite phase. If one comes down, another will be going up, exactly opposite. As you walk, your hands will be going in 180 degree out of phase. When your right hand moves forward, left hand will be going back. Similarly, here the particles, when this goes above, this will be coming below. So what is the phase difference between them? That is pi. Now, do you get that using this formula? Phase difference equal to 2 pi by lambda into path difference. Path difference between these two particles is lambda by 2. So put lambda by 2 here in the place of path difference. Then lambda gets cancelled, 2 gets cancelled, pi. Now, shall we check it for a path difference of lambda? If two particles are separated by a distance of lambda, they should have a phase difference of 2 pi. Substitute it here. Phase difference equal to 2 pi by lambda into path difference lambda. Lambda gets cancelled, and this is 2 pi. And if the path difference is lambda by 4, here, these two particles, they have a phase difference of pi by 2. They are like sine theta and cos theta, right? Whatever I have explained in one of the previous class. So do they have a phase difference of pi by 2? Yes, you can substitute in the formula. Phase difference equal to 2 pi by lambda into path difference is lambda by 4, 1/4 of the full lambda. So lambda gets cancelled. 2 by 4 is 1 by 2, pi by 2. So you can get any phase difference if you know the path difference. Similarly, if you know the path difference, you will get the phase difference. Just change the formula. Lambda by 2 pi into phase difference gives the path difference. And this we have seen, if two waves superpose, if the crest exactly falls on the crest, then so now this case here, yes, crest falls on crest, you get maximum amplitude. If the crest falls on trough, you get 0 amplitude, and the resultant wave will be 0. There is no wave at all. You see, crest exactly falling on trough. In some other cases, the crest will not be exactly falling on crest, and then you get a resultant wave of neither maximum nor minimum amplitude. If two forces, 4 Newton and 3 Newton, are made to act in the same direction, maximum resultant 7 Newton. If they act in the opposite direction, minimum resultant 1 Newton. If they act at different angles, you will have different results. In the same way, here, if you can see that throughout here, we have seen this, and we have seen this also. Intensity of a wave is 2 pi squared f squared a squared rho v. I will go through this. Yes, this is also over. This one is over. Yes. Now, this is what we were concentrating on. This is what you should know very clearly. We have explained it. If there is a wave of amplitude A, and if there is another wave of amplitude B, and if they superpose with zero phase difference. What do you mean by zero phase difference? The crest of one wave falls on the crest of another, exactly. Trough falls on trough, exactly. Then the resultant wave will be maximum, and the amplitudes will add up. Now, what is the intensity of this wave? Suppose you go to the previous formula, the intensity of a wave, 2 pi squared f squared a squared rho v. The single wave has an intensity I proportional to a squared. This has an intensity proportional to b squared. What is the intensity of the resultant wave? It is a plus b whole square. So intensity will be directly proportional to square of the amplitude. So if amplitude of this is a, for example, amplitude of this is b, then this intensity is a squared, this intensity is b squared. When they superpose, they produce a new wave of highest amplitude. Intensity is proportional to a plus b whole square, because amplitudes add, but intensity grows square of the amplitude. Okay, if these two waves superpose with crest on trough like this, with a phase difference of pi, because this starts a little bit earlier and this starts a little bit later. Now the phase difference is a minus b, and if a and b are almost equal, then the intensity will be 0. And suppose the two waves start from the same point, no path difference is 0, because both the waves have to travel equal distance and reach here. No path difference, and the path difference is 0, phase difference is also 0. So they interfere constructively, producing maximum amplitude wave there, right? So, and when you will get destructive interference, if the path difference is 1 lambda, by the time the two waves reach here, one wave travels a lambda by 2 extra than the other wave. So if the path difference is, so this point is very important for today's discussion. You are going to apply it in two cases now. So if the path difference is lambda by 2, half lambda, what do you mean by that? If one of the wave travels half lambda extra than the other wave before it meets the other wave, then that results in the destructive interference. Because by the time this wave completes lambda by 2 extra journey, it meets the crest in the trough of this position. So one wave produces crest, another produces trough, one produces compression, another produces rarefaction, and if the amplitudes are same, then you will not have any resultant wave. So if the path difference is 1 lambda, lambda by 2, destructive interference. If the path difference is 1 lambda completely, if it is 1 lambda, again crest meets the crest. So if one wave travels 1 lambda extra, by the time it meets the other wave, the crest of that wave matches with the crest of another, trough meets with the trough, and the resultant amplitude will be maximum, vibration will be maximum, and the wave grows. We will get maximum wave there. If in terms of sound, you will hear maximum sound. In terms of light, you can see maximum light there. Okay. Suppose the path difference, again, this is 1 lambda, half lambda, 1.5 lambda. If the path difference is 1.5 lambda, that is 3 lambda by 2, again destructive. So you'll have to know all these conditions. When the path difference is exact 2 lambda, again constructive. So that can be understood here. So we will put in an equation form. If the path difference is 1 lambda, so this wave is starting 1 lambda later, right, than this. And if the crest falls on crest, constructive. If it is 2 lambda, you see this wave starts by the time this completes 2 lambda. So by the time these two meet, then crest falls on crest. So if the path difference is 1 lambda, 2 lambda, 3 lambda, n starting from 0, 0 in the sense both start from the same point, then it leads to the constructive interference. The two waves superpose, producing a resultant of wave of highest amplitude, highest intensity. So shall I put it like this? Path difference is n lambda. But how is the phase difference? What is the phase difference? Now, if the one wave starts from here and another wave starts lambda later, what happens is there is a phase difference of 2 pi, because this has started its journey or vibration after 2 pi. So the first phase difference is 2 pi. Next one is 4 pi. It is an even multiple of pi. 1 lambda corresponds to 2 pi. 2 lambda corresponds to 4 pi. So how to write it? It is 2n pi. So how do you get it? You can use a formula again. Phase difference phi is equal to 2 pi by lambda into path difference. Path difference is n lambda. So lambda lambda gets cancelled. It is 2n pi. N equal to 0 corresponds to 0 pi or 0. N equal to 1 corresponds to 2 pi. N equal to 2 corresponds to 4 pi. So this condition is the condition for interference, constructive interference. So if you want crest to fall on crest, if you want the amplitude should grow, or if you want to see a light which is of highest amplitude, or a sound of highest amplitude, or a water ripple of highest amplitude, if crest has to fall on crest, the two difference in the distances traveled by the two waves must be n lambda, or they should have a phase difference of 2n pi. So this condition you shouldn't forget anywhere. If the path difference is n lambda and if the phase difference is 2n pi, then it leads to constructive interference. That means the waves interfere constructively to produce a large wave of highest intensity. What about destructive interference? It is here. For destructive interference, you see, if one wave starts here and the second one starts after lambda by 2, the second wave starts after lambda by 2, what happens here is, here you can see that lambda by 2 difference, crest falls on trough. If these waves superpose, then they produce destructive interference, because one produces compression, another produces rarefaction. One says to compress, right? The air gets compressed due to one wave. Due to another wave, air gets rarefied. So if both instructions are given simultaneously, what the air molecules will do? They don't vibrate at all. And so resultant amplitude will be 0. So for destructive interference, path difference is n plus half lambda. N equal to 0 corresponds to lambda by 2. N equal to 1 corresponds to 1.5 lambda. N equal to 2 corresponds to 2.5 lambda. That is 5 lambda by 2, so on. So what is the phase difference between such particles? If it is half lambda, then it is pi. If it is 1.5 lambda, it is 3 pi. So it is odd multiples of pi. So find out the phase difference. Phase difference between the two waves which have the path difference of half lambda, 1.5 lambda, 2.5 lambda, etc. is 2 pi by lambda into path difference. Path difference is n plus half lambda. Now, if you bring this 2 inside and if you cancel lambda, what you will get? Pi outside, yes. 2 inside, 2n plus 2 by 2. That is 2n plus 1. 2n plus 1 pi. Lambda gets cancelled. So, if the phase difference is 2n plus 1 pi, path difference is n plus half lambda, then it's a destructive interference. So, try to remember these 4 conditions. 2 conditions for constructive, 2 conditions for destructive. They are very important. Okay, hope you will follow this now. Now, we will have a few more things to clarify. Yeah, and you know, intensity of a wave is 2 pi squared f squared a squared rho v. So wherever the amplitude becomes larger, there the two waves must have fallen with crest on crest. So it should be a plus b. What is the intensity there? A plus b whole square. What is the minimum intensity? A minus b, because there the two waves must have met with the crest on trough. A minus b. Suppose a minus b, if a and b are equal, intensity is 0. If a and b are equal, this will be 2a whole square, that is 4a square. That things, those things you are going to study in detail. So this is an experiment to show the interference in water. What you have to do is, you should produce 2 water ripples at the same time. The 2 water ripples will travel. Wherever they superpose, they don't produce their own characteristic. They produce a superposed characteristic. You can clearly see that here. So a person is simply making the water to vibrate using a ball, and he is producing one ripple, and at the same time he is producing another ripple. Now the single ripple joins with the other one. You see, at some places water vibrates with highest amplitude. At some places water will be depressed, right? That means it vibrates with negative amplitude. At some places there is no vibration at all. So you can see the interference pattern. The two waves superpose on each other. At some places you get maximum intensity. Here the intensity in the sense water ripple will be having highest crest or highest amplitude. At some places water ripple will not be produced at all. It will cancel. You can see at some places there won't be any wave at all. So this is the superposition principle, and that happens regularly at different places. Hope you can get the idea, right? When only there is a single wave, you have circular wave fronts, right? Ripples moving all around. But when another wave is produced, they superpose on each other. So when they superpose, at some places crest may fall on crest, at some places crest may fall on trough, and at the places where crest falls on crest, wave will be of highest amplitude. The places where crest falls on trough, there will be no wave at all. So that's how it is produced. You can see that very clearly in the water. So this is about water ripples. Suppose the two waves are of sound waves. At some places you can hear maximum sound. At some places you don't hear any sound at all. And in the case of light, at some places you will hear maximum, you can see maximum light. At some places you don't see light at all. That is what happens when two light waves superpose. But the thing is, you can't see light so easily as you see these water ripples, because light has a very small wavelength. You can't notice it. You should use a microscope and you have to make the two waves to superpose. So many conditions have to be satisfied in the case of light, since its wavelength is very less compared to the wavelength of these water ripples. Okay. This is Thomas Young's double slit experiment. Already we studied that Thomas Young did one experiment and showed that light can superpose. When two light waves superpose, at some places, the crest of one light wave falls on the crest of another light wave, and that produces a brightest high intensity light wave. At some places, crest of one wave falls on the trough of another light wave, and no light can be seen at such places. And the clear explanation of that interference pattern was given by Thomas Young using Huygens wave theory. So that was a very good support to the wave theory, which says that light is a wave. So what did Thomas Young do? He took a cardboard and he made a hole here, and he made the light to pass through this hole, and that is a single source of light now. For interference, you need two sources, right? The two sources must have a phase difference or path difference and something like that. Now, in front of the cardboard, he took another cardboard and made two holes in that, very fine holes. So one cardboard was taken, and in front of that, a source of light was switched on. Light came out of this, producing wave fronts, and that light is made to pass through one more cardboard having two holes. Now, this acts like two sources of light. But both these sources are coming from the same parent source, so they must be identical. That means their amplitude must be same, frequency must be same, and wavelength must be same, because they are generated from the same parent source. Now these waves from here are made to fall on a screen. Imagine that this is a screen, and on the screen the light wave from here can go and meet the other wave from here like this, and on the screen light wave from here can go here and meet the other wave here. So on the screen light can meet the other light from one slit can meet the light from other slit by traveling different distances. Now what that path difference, you can clearly get the idea here. You see, imagine one secondary wave, and according to Huygens, as soon as the light falls on this slit, this small opening in the cardboard, this small hole in the cardboard, when the light comes from this small hole, every point of the hole act like a secondary source. Light will be emitted in this direction, light will be emitted like this, light will be emitted like this. So secondary waves travel in all directions. Now consider this point, which is at a perpendicular bisector of these two holes, or these two slits. Very fine holes they are. The light coming from this is having a identical characteristic with this light coming from here. So draw a perpendicular bisector. Now the distance from here to here, here to here are same. Now you ask the waves once they meet here, you just talk to them. Both the waves say, sir, I have traveled some distance. My friend also has traveled equal distance, sir. So by the time they meet here, when the wave from here travels here and wave from here travels here and meet here, they should meet with the crest on crest and trough on trough. Why, sir? Because there is no path difference. If the wave from here travels a certain distance, same distance will be traveled from the other wave here also, because this lies on the perpendicular bisector. Since it lies on the perpendicular bisector, the distance should be same, and here you should get a bright light. Since we are talking about light, it is not sound, it is not water ripple. When light with the crest on one wave and falling on the crest on the other, trough on trough, light wave should have brightest intensity because amplitudes add up. And if the amplitude of this light is A, amplitude of this is also A because they are identical slits, then the total amplitude by the time they reach here is 2A. If the intensity of this wave is square of the A and intensity here is proportional to square of A, intensity here is directly proportional to square of 2A. That means 4A square. So what has happened to the intensity? Intensity of this is proportional to A square. Here it is A square. Here it is 2A whole square. That is 4A square. Intensity of this light will be 4 times the intensity of these two individual waves. It will be the brightest point. Now, I can proceed and I can show it to you that these waves are traveling like this. See, one wave started here and started here, and one by one the waves will move. Of course, you can't see the light waves with such a clarity because the wavelength is very less. This is only a demonstration to show what happens here, right? Now see the first wave and the second wave. How much they have traveled? This wave says, Shar, I have traveled a distance of 5 lambda. What about here? 5 lambda. By the time they meet here, since they are identical, the crest of this should fall on crest of another. Of course, when they fall, they should not fall with such a large angle. And all these diagrams are drawn to just for understanding purpose, drawn to make the students get understood. That's all. And they shouldn't fall with such a large angle. But still, you can see crest falling on crest almost here. This gives the constructive interference, and this is called central bright fringe. And here you get bright light. Now, suppose you select a point not on the perpendicular bisector here, not at the midpoint of the perpendicular line drawn to these two sources. Just go away. What will happen? If you move a little bit away, of course, I can explain this in terms of two friends walking. Suppose from here, a person is walking towards this point, and from here, another person is walking towards this point, and both of their footsteps are equal in size. So what will happen by the time they end up here? This person walking here and this person walking here, both putting the same type of footsteps. By the time they end up here, both of their footsteps will coincide. Is it so? Just for understanding, I am doing it like this. Suppose this person starts walking towards this point. So one step over, right? One step, second step, third step, fourth step. Finished. What about this person? So 4 steps. What about this person? He has started one step, second step, third step, fourth step. The steps coincide. Is it so? This is constructive interference. So when they reach here, they will be reaching with the identical phase. And PHASC phase, right? They are reaching in phase. That means both of their fourth step will clearly end up, and both of them will be putting their footsteps at the same point. That is what you call constructive interference. And if the amplitude, crest of one wave exactly falls on the crest of another wave. Suppose these two are sound waves. Suppose these are identical speakers, for example, identical tuning forks. If you stand here, you will hear maximum sound. Just think of sound waves. You switch on a speaker here, switch on a speaker here, or switch on a tuning fork which produces sound, and another identical tuning fork here. Identical in the sense their compression and rarefactions are equally spaced. Wavelength must be same. Now, when the compression, rarefaction travels here, suppose this is the fourth compression here. For this wave also, it is the fourth compression. What will happen to the air in this region? It will be compressed very much, right? Because both are asking the air to compress. So compression will be highest here. And if the rarefaction of this wave ends here, then the rarefaction of this wave also ends here. And this will produce the highest rarefaction. That means air here is compressed to the highest extent, rarefied highest. So here if a person is sitting here, he will hear maximum sound. So this is constructive interference, that is central bright fringe. Simply for explanation, I have taken these steps. You can take light as a very small kid with the small footsteps in the range of nanometer or micrometers, right? So very small footsteps. Okay. Now, suppose you select a point somewhere here. Now comes the path difference. Now you can understand what is actually path difference. Because you see, imagine the persons are not traveling to the perpendicular bisector here, not equal distances here. Now there is a chance that A person walking from here to here and here to here, again their footsteps may end up identically, in the sense they are not keeping the equal number of footsteps, but this person may keep some 10 steps and this person may keep some say 6 steps. Of course, the 6th end step and the 10th last step may coincide. We know that the crest and trough of the first number itself need not coincide. Some crest should fall on crest only. That's all, whatever be the number. Now let us see. Again, we will search another point where crest falls on crest or footsteps coincide. This person has started its journey. First step, second step, third step, fourth step, fifth step, ended. What about this person? Okay, he has ended 5 steps. What about this one? First step, second step, third step, fourth step, right? His fourth step is coinciding with the 5th step. Whatever it is, crest is falling on crest. And this is again constructive interference. You will get maximum light again. So you got maximum light here and you got maximum light here. Sir, that means throughout you have maximum light? Not possible, because if you consider a point here, definitely it is maximum light because the 2 waves are traveling identically and there is no path difference, maximum superposition. And this is another point where you get maximum superposition. That is 1 lambda path difference. Can you understand it now? When you displace the 2 waves, I have shown that 1 wave moving forward, and when the distance difference, path difference is lambda by 2, there was a destructive interference. You can remember that, you can recall that slide. And when the distance difference is lambda, again there is a constructive. But between 0 and lambda, there is a condition in between where the crest is falling on trough, that is lambda by 2. There you don't get a wave at all. That means here you get maximum sound, here you get maximum sound, here you get maximum light, here you get maximum light. In between you should have 0 light. Where it is? Let us see. This person. So I have seen this. We have discussed this one, right? We have discussed this one. Now we will see an in-between point. Yes, here. This person, first step. So for a clear understanding, I have taken some long steps here. So he has completed third step, right? 3 steps. 1, 2, 3. What about here? 0, 1, 2. Third step will be here. His third step goes here. What about here then? 2.5. Correct? It is 2.5 steps. What is the result? That means this person might have raised his leg. He hasn't put the step at all. His leg is at the peak now. This person has ended his step. That means the crest of this is not falling on the crest of this. It is the crest falling on trough. Destructive interference. It is half lambda. See the difference between the steps? Half lambda, right? If we take this as 1 lambda, 2 lambda, 3 lambda. This is 1 lambda, 2 lambda, 2.5 lambda. 2.5 lambda minus this 3 lambda, that is half lambda difference. That is destructive. So destructive. This is the first dark fringe. So if you get maximum sound here or bright light here, if you get another bright light here which gives you a path difference of 1 lambda, in between you get a point where the path difference is half lambda, where you get destructive interference. So imagine a cardboard kept like this and 2 holes made on that, very fine holes, and a screen placed here. Won't you get maximum light here? As you move away and away and away, the brightness goes on decreasing, it becomes 0 here. Again the brightness goes on increasing, becomes maximum here, again decreasing. Just like 2 waves displaced, when the 2 waves are coinciding each other, 0 path difference, maximum interference, crest falling on crest. When the other wave is slightly moving, when the difference is half lambda, destructive. When the difference is 1 lambda, constructive. When the difference is 1.5 lambda, again destructive, constructive, like that, right? The same thing happens here. So you might have got the doubt when I was discussing about those 2 waves, when the one wave is displaced from the other wave. Sir, where do we get all these things? This is the best place. You can see it here. So when this source and this source is switched on, light from the 2 sources can travel different distances. Here when they travel, this wave has to travel larger. This wave has to travel smaller. How much larger and how much smaller? If that larger distance minus smaller distance is equal to 1 lambda, 2 lambda, 3 lambda, 4 lambda, then this point will be a bright fringe. And if this larger distance minus smaller distance, what I call path difference, is half lambda, 1.5 lambda, 2.5 lambda, 3.5 lambda, then that point will be a destructive point. That means there you don't get sound, you don't see any water ripples, you don't see don't hear any sound, you don't see any light. So this is how the interference can occur between the two waves. So you will get all types of waves superposing. So if you go on walking on the screen and asking all these waves and ask them how much distances you have traveled, both the waves, then both the waves will give you different answers when you go to different points on the screen. When you are exactly at the perpendicular bisector, the two waves say, sir, we have traveled equal distance. When you go just here, they say, sir, we have traveled a difference of half lambda. When you go here, they say, sir, we have traveled a distance of 1 lambda, 1.5 lambda, 2 lambda, like this. So you will get all types of interference on the screen here. So that is the beauty of interference. Now we will go to the real light. Of course, with virtual animation, not real animation. Now you see these two lights, whatever be the wavelength of these two sources, they must fall on identical with the identical phase. If this wave travels a certain distance, the same distance will be traveled by this wave also. Then that leads to constructive interference. We see the brightest light here, right? Now select another point here where this wave travels at a lesser distance, this wave travels more distance, and the difference is 1 lambda. That is why we got again bright light here. This is the very next bright light produced after this, and this is called central bright fringe. This should be bright, and this is the next bright fringe. In between you get dark, where the distance traveled by this wave and distance traveled by this wave have a path difference of half lambda. This is the gist what I wanted to make you clear from 3 days. From 3 days, I have been crying about phase difference, path difference in 3 different lectures. And today, I want you to make it very clear about all those things. So finally, in the 3 hours or some about 2 and 2.5 hours, what I was struggling to make you clear is, this is here, there is no path difference, bright fringe. Path difference 0, phase difference 0. Here the two waves, by the time they meet here, path difference is half lambda and phase difference is 1 pi. That means crest falling on trough, dark fringe, no light here. And when I go here, this wave travels more, this wave travels less, difference is 1 lambda, again bright. Can you tell me what is here? Here at this dark, this is the second dark from here to here. So when the wave travels from here to here, when the another wave travels from here to here, this has to travel more than this one. How much more? 1.5 lambda. And what about here? That is bright, 2 lambda difference. This is the beauty of interference. So you will get all types of interference patterns here. You will get different points where the two waves have traveled different distances. Now, suppose this is the brightest point. This is the darkest point. In between you have neither dark nor bright places. Why it is so? Because crest is not exactly falling on trough, or crest is neither falling exactly on crest. These are the points where crest is neither falling exactly on crest nor on trough, because there are some intermediate intensities also. For example, when I was saying if the resultant of two forces is root of a square plus b square plus 2ab cos theta, then in such a case, if A and B, two forces are 4 Newton and 3 Newton, always you don't get 4 plus 3 Newton equal to 7 Newton. Always you don't get 4 minus 3 equal to 1 Newton. Sometimes when the forces are in the same direction, you get answer 7. Sometimes when the forces are in the opposite direction, you get the answer 1. But if the angle is different, angle between the two forces is different, like 60, 90, 80, something like that, then the answer will vary from 1 to 7, right? It will be in between 1 and 7. Best example is when the forces are perpendicular, 4 Newton and 3 Newton. Resultant is 5, root of 4 square plus 3 square, because 2ab cos 90, that part will be 0. Root of 4 square plus 3 square will give you 5 answer, which is in between 1 and 7. So such points are where you get the intensity is neither very bright nor very dark. So such points are also possible. So, but we are discussing only brightest point and darkest point. That's all. Okay. Now, yeah. Now, if you ask me, what is the path difference between these two waves, sir? See, this is the second bright fringe, right? This is central one. For the central bright fringe in the Young's double slit experiment, condition is path difference equal to 0 lambda. The wave which has traveled from here and have traveled from here must have traveled equal distance. No path difference. They should fall. Both the friends must have traveled equal footsteps, and their footsteps should match. And here there should be bright point, right? Now, what is the path difference here? What you have to do is you remove this much of distance from this one. The remaining is the path difference. And this, since this is the very next bright fringe, here the path difference should be 1 lambda. Recall that slide where we have made two waves to fall on each other and both were traveling equal distance. And when one wave is displaced, again we got crest falling on crest when the difference between the two waves was 1 lambda, correct? So this is the place. This should be 1 lambda. And the rest of the distance is equal, right? The rest of the distances are equal. Now, can I draw a diagram for this one? I am trying to make you very clear without animation itself. Sometimes I will be explaining. Then I will be showing animations so that it will be, you will build your own model inside your brain, right? So this is 1 lambda. Now, what about this one? Now this starts, okay? If I go on explaining the waves like this now, so this is 1 lambda, yeah, you see, 1 lambda, 2 lambda, 3 lambda, 4 lambda, and 5 lambda distance, say. What about this wave? It travels only 4 lambda, 1, 2, 3, 4, yes, crest falls on crest. This is the pairs where the path difference is 1 lambda, constructive, whereas here 0 lambda, no difference. No difference in the path. Here there is a path difference, but it is 1 lambda, but crest falls on crest, constructive. Now you take another case. Okay, here 1 lambda, yeah, 1 lambda, okay, crest falls on crest, right. Now take another case, 1 lambda, 2 lambda, 3 lambda, 4, 5, 6. Okay, what about this one? 1 lambda, 2 lambda, 3 lambda, 4, 5, this is 6.5, right? This one is 6.5. Yeah, 6.5 lambda, right? Can you get that? This one has to travel 6.5 lambda. 1, 2, 3, 4, 5, 6, and then half is required here to reach here. This is 1, 2, 3, 4, 5. Now what happens? Crest falls on trough, destructive. Here it should be a dark fringe. That means if the path reference is half lambda, destructive. Then here you may get some point where the path reference is 1 lambda. Okay, now we will go to some 3 problems. We will make this point very clear. If you again ask me again, as I was saying in at the end of the last class, if you ask me again, sir, how many marks questions will be asked out of what you did now in wave optics? I don't know. It is only 2 marks, 1 mark. You may be asked to write what is the Huygens wave theory, what are the points, and what type of wavefront you will get from a point source or a linear source. What is the type of wavefront when you are at a large distance, and what are the conditions for constructive interference? What are the conditions for destructive interference? From the 2 or 2.5 hours, I have completed only a few 2 marks questions or 1 mark question. That's all. But if you are very clear about what is interference, then I think what my purpose is served in this video. And if you get the clear idea of this, then the rest of this chapter is nothing to you. You can move away like anything. And even the problems, what are all the glitches given in the problems, you can understand it very clearly once you know all these things. Otherwise, you can never touch the problem of this chapter. In a dry way, you can by heart all the things, but you will never understand deep into this. Now we will go to these problems. I hope after solving these 3 problems, everything will be clear to you. Let us see that. So this is my new attempt in making the students to understand about interference. I'll try my level best. Let me see what will happen. Please respond to me after once you finish this class. Please respond to me if you still have any doubt, or even if you have understood, please respond to me. You know my number 94801 98001, right? 94801 98001. But you should have listened to all the 3 lectures, previous 3 classes, I mean especially previous 3 classes. And if you are very clear in of course, up to some extent, of course, we can't learn everything that is in nature, but still, if you have understood interference to some extent, please message to me that, sir, I have understood it, whatever the explanation given by you. Then I feel satisfied. And if you have not understood, whatever the doubts you have, you put it to me in WhatsApp. I will answer it to you. Because if you have plenty of doubts still remaining, that means that something is going into your brain, right? If you have not understood anything, of course, you will not have any doubts also. Yes. Now, read the problem. 2 loudspeakers are situated at A and B and are separated by a horizontal distance of 6 meters. Everything is given in the diagram. So this is, and imagine your classroom. You are all sitting here, okay? You are all sitting here. This is the stage where the teacher is moving here and there, and this is the board. On the 2 corners of the board, which are separated by 6 meters, there are 2 speakers, sound speakers. Those 2 speakers are situated at a horizontal distance of AB. Horizontal means parallel to the ground now. O is the midpoint of AB. Okay, this is the midpoint of the board. And a detector of sound is moving parallel to AB. So somebody is moving parallel to the desk kept here. So there are sets of desks and you are sitting all over here. So your friend is moving from here to here. Somebody is moving from A to B. Okay, parallel to AB here in front of the board. A detector of sound is moving parallel to AB. So somebody is detector of sound because we have an instrument which can detect the sound called ear, right? So ear can detect the sound. So you have to move from Q to P or P to Q or up to this. Somewhere here you have to, you should keep on roaming around here. Okay. A detector of sound moving parallel to AB at a perpendicular distance of 8 meters. So this is 8 meters at a perpendicular distance for the line joining these speakers. To the line joining the speakers at a perpendicular distance, you are moving here. Detector moving parallel to AB at a perpendicular distance of 8 meters. This is given. Records a maximum sound at P. Now can you understand? Here, when the detector is here, your friend, when he reaches here, he says, sir, I am hearing maximum sound. Maximum sound is recorded at P. That is 100% sure. Even in the problem, it need not be told because we know that what the sound is traveling from here to here. If it produces rarefaction here, this sound should also produce rarefaction because they have told 2 loudspeakers. Of course, I should have added 2 identical loudspeakers. Only when the footstep of this person and footsteps of this person are identical, then only their footsteps will match here. Otherwise, it won't be, right? If the footstep of this person is not 1 feet, suppose it is 1.5 feet, and the footstep of this person is some, say, different, 0.8 feet, then that doesn't match. But you have to take it as loudspeakers are identical, okay? So this should be a maximum sound point because if this produces rarefaction, this should also produce rarefaction, no doubt. Here, if this produces compression, this should also produce compression, no doubt. They should match here. Of course, let us move on in the problem. That records a maximum sound at P, which is vertically opposite to O. Okay, we know it. And another maximum sound at Q, which is vertically opposite to B. So another maximum sound is heard here. That's what they say. Remember, this is a JE level problem, but no calculator needed. Even no pen is required. You can solve it now if you have understood what is interference. Now, the second maximum sound can occur anywhere. That we don't know. The second time the footsteps may match anywhere. That we don't know. That depends on the length of the footstep. Now, they say that in the problem, another maximum sound at Q is heard here. Another maximum sound is heard at Q, which is exactly opposite to B. Now, what is the wavelength of sound? So the clue for us is, if the first maximum sound is heard here, there is no path difference for the 2 waves. If the very next maximum sound is heard here, they should have a path difference of 1 lambda. Because you know, when you displace one wave, when there is a displacement of half lambda, destructive. When the next maximum, that means Next crest falling on crest occurs when there is a path difference of 1 lambda. That means if these two waves have no path difference here, next crest falls on crest when there is a path difference of 1 lambda. That means this distance minus this distance should be equal to 1 lambda. Do you agree? Sir, next is mathematical. This distance, this wave has to travel 1 lambda extra than this wave. Otherwise, again, you won't get crest falling on crest. First one occurred here. Next one occurs here. So what is this distance? This distance is simply Pythagoras theorem. 8, 6, right angled triangle. Root of 8 square plus 6 square. 8 square is 64. 6 square is 36. 64 plus 36 is 100. Root of 100 is 10. This is using Pythagoras theorem. This is 100. Square root of 100, that is 10. 10 minus 8. Path difference, 10 meters, 8 meters, 2 meters. That is 1 lambda. Because this must have traveled 1 lambda extra compared to this wave. That is why again crest has fallen on crest. So path difference is 1 lambda here, since it is the very next bright fringe, very next maximum sound production point. So wavelength is 2 meters. This is the answer. This is a problem which is good enough to be asked in JEE level. And once you know the theory, this is having no calculations at all, only physics background. Okay, answer is second one. We will move. Okay, so this is the way in which you can analyze it. The two sound waves can travel like this, and the crest may fall on crest here. This is the central maximum production, right? Here you will get maximum sound, where here. And the next maximum sound is possible here also. Again, the some sixth crest and fourth crest may fall. Here it is a sound wave. Some sixth compression and fourth compression may fall on each other, or sixth compression and fifth compression may fall. So that is possible, right? That's how the sound travels. Okay. So answer is AQ minus BQ must be equal to n lambda for the first bright fringe. Of course, this corresponds to n equal to 0. This corresponds to n equal to 1, n equal to 1 lambda. And this is 10 due to Pythagoras theorem, and this is 8 must be equal to 1 lambda. Lambda is equal to 2 meters. Second option. Now you see this problem. A sound wave of wavelength 32 centimeter enters the tube at P, as shown in the figure. Okay, a sound wave enters here. Say I will hold a tuning fork here. Sound waves, they are the disturbances that are traveling in air. They move in, but here they split into two parts, because there is a path here, there is a path here. So compressions and rarefactions travel here and travel here, and by the time they reach here, they superpose again. The same wave starting from the same parent, and they split and again join. Now, the minimum value of radius of R, suppose radius R. So this radius, what is the minimum value of R, for which the sound at Q is maximum. If you want to hear maximum sound here, that wave which has traveled like this and reached here, and that wave here which travels here, if you want to hear the maximum sound, they should again fall with crest on crest. But the problem is here, the wave, when they travel together, of course, they are the kids of the same parent. But now when they split here, they will have different characteristics, because this wave has to travel more distance, whereas this wave has to travel less distance. When this travels more distance and reaches here, this travels less distance compared to this and reaches here, don't know whether crest falls on crest at all. There is no chance. There may be a chance of crest falling trough also, but they are asking you the minimum value of radius. How much should be the radius, so that sound at Q is maximum. The sound heard here should be a maximum sound. Now, for that one, imagine two friends walking from here, having equal footsteps length, right? When they walk up to this, their footsteps will be matching. Say two soldiers. By the time the one soldier reaches from here to here, another soldier continues the journey in the same direction. We don't know whether their footsteps match each other or not. That depends on how much extra this person has traveled. Suppose the footsteps are 1 feet, exact 1 feet. Suppose this distance is 10 feet and this is 12.5 feet. By the time this person reaches here, his footstep will end up with half feet, right? This one will be full feet. They won't match. That means you should go for path difference now. By the time the ray which has split from here to here and has moved from here to here, and the way which has traveled straight, will have a path difference. What is that path difference? They are asking you minimum value. What do you mean by minimum value? Very next. That means if you have two waves superposing on each other, there is no path difference. Now start sliding the one wave over the other. What is the first condition where you get again crest falling on crest? It is for 1 lambda, right? Once you displace for half lambda, crest falls on trough. Again crest falls on crest for 1 lambda. So that means this difference, that means this wave which travels extra distance minus this distance must be equal to 1 lambda. That is the minimum condition. So what are those distances? So can I write this distance as 2 pi r by 2? 2 pi r is the circumference. This distance is only 2 pi r by 2, half of the circumference. What is this distance? That is the diameter, 2r. So 2 pi r by 2 minus 2r must be equal to 1 lambda. Do you agree that now? This path minus this path, that difference is 1 lambda. Then again you will get constructive here, maximum. So shall we write the path difference? That is, this one is 2 pi r by 2 and this is 2r. So that difference we will write it. 2 pi r by 2, this path minus this one, 2r, must be equal to the minimum condition, that is 1 lambda. Once the two waves start producing path difference, the minimum path difference at which again crest falls on crest is 1 lambda. Okay, so if you analyze this, I think I can cancel 2 and 2 here. Pi r and minus 2r, r can be taken outside, pi minus 2. So pi minus 2 into r, it is equal to 1 lambda, and pi is 3.14, minus 2 is equal to 32, lambda is given, 32 centimeter. Now this 3.14 minus 2 is 1.14, so what is r? 32 by 1.14, and 32 by 1 is 32, right? 32 by 1.14 is slightly less than 32, that is 28. This should be the answer. You can check it using calculator, but in the examination, calculator will not be given. So this should be 28 centimeters. That means, what is the meaning of this? Because we are not discussing entrance exam classes. What is the meaning of this 28 centimeter? That means the distance, the radius of this must be at least 28 centimeters, so that when the wave traveling from here extra and this wave traveling from here to here will meet with again crest on crest. So if they have traveled together straight, of course, they might have traveled always with crest and crest. Since there is a path difference occurred, if the radius of this tube is, if it is 28 centimeter, again they will fall with crest and crest here. Again, you will get maximum sound here. That is the meaning. We will take up one more beautiful problem here. Now, for the understanding of interference, you see here, two sources are placed on x-axis at a separation of d equal to 3 lambda. So over x-axis you place two sources and they should be separated by 3 lambda, where lambda is the wavelength of that those sources, whether they are light sources, of course. An observer starts moving from A on a circular track of radius r much greater than d. How many bright points and dark points will be observed? Of course, he observed. Also find the angular position of maximum and minimum. This is the direct diagram given for this problem along with the problem. Now you can understand the sentence. Two sources are placed in the x-axis. Distance between them is taken as small d, that is equal to 3 lambda. And there is an observer who starts moving from A. Where is A? Here. He starts moving from A and keeps on walking like this to B, and then to C, and then to D, and then back to A. As he moves from here to here like this, he receives light from here to here. Imagine that these two are the sources of sound, and he receives sound here from both the sources. By the time he reaches here, he receives sound from both the sources, or light from both the sources, because we have two instruments in our body which can detect sound and which can detect light, so no problem. And by the time he reaches here, he receives the light from both these sources. Now their question is, he moves on a circular track of radius capital R. Where is R? Here is R. R is much greater than D. These two sound waves are separated, sources of light are separated by a very small distance compared to the radius. How many bright points and dark points will he observe? So as he moves from here to here, looking into these two sources, the light received by him will go on changing. It will produce bright light and dark light as he moves. Suppose he is holding a detector, and if he is moving like this, how many bright points and dark points he will observe? and bright point means maxima, and dark points means destructive interference minima, as he completes one full circular path. Very easy problem. Just I will tell you, because if I give you some 3 or 4 ideas, then you can move forward by yourself. Now, how to analyze this? Of course, some few ideas might have started entering into your brain, right? But you may not be knowing how to put it into a proper form. Now, very easy. When the person is here, you search for a point where both the waves have to travel equal distance towards him. When he is here, this wave and this wave have to travel equal distance, because these two sources are placed symmetrically about origin. So now we will see how the waves are traveling from this. From here they have to start here, and here they have to run here. Okay, they will travel equal distance. So can I say that this is the point where there is no path difference, right? Suppose this wave travels 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, like this. What about this one? 1, 2, 3, 4, 5. Crest falls on crest, brightest point. No path difference. Now let the person be here at A. What is the difference now? Now, from when the person is at A, light from here has to travel longer distance. Light from here has to travel lesser distance. Let me show it at different points. Now you see here. This light has to travel 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6, 7, 8, 9 lambda. What about this one? Now you know that the distance difference between this wave and this wave definitely is this one, right? S1 to S2 distance is the extra distance that S1 has to travel by the time it has to reach A, whereas it has to travel S2A. However, S2 has to travel S2A. S1 has to travel S1A, but S1 has to extra compared to S2. What is this distance given? It is already given 3 lambda. This distance is 3 lambda. So is the path difference by the time the two waves reach here 3 lambda? Definitely, isn't it? So I have shown that 3 lambda in terms of like this: 1, 2, 3, 4, 5, 6, 7, 8, 9 lambda. Here this has to travel 6 lambda. 1, 2, 3, 4, 5, 6 lambda. Difference is 3 lambda. Of course, I need not go for this diagram in order to say that it is 3 lambda. Already given this distance is 3 lambda. That means when the person is here, he is receiving the two waves which have a path difference of 3 lambda. When the person is here, he is receiving two waves which have a path difference of 0 lambda, right? Here 0 lambda, here, so I have written 0 lambda path difference, here 3 lambda path difference. Then where is 1 lambda and 2 lambda? They must be somewhere here in between, right? So there should be a point here such that by the time this wave travels here and reaches here, this wave travels from here and reaches here, they should have a path difference of 1 lambda. There should be a point here which is 1 lambda. Am I right? There should be a point here which is 2 lambda path difference. This distance traveled by this wave, this distance traveled by this wave, they should have a path difference of 2 lambda. So there are all the waves, because this is 100% 0 lambda, no difference. This is 100% 3 lambda, because this itself is given for us. In the problem it is given d is equal to 3 lambda. That means 1 lambda, 2 lambda should lie somewhere here. That means when the person is here, he will receive maximum light, because third crest of one wave falls on the first crest of another, right? Whereas here second crest of one wave falls on the first crest of another. Crest falls on crest. This is the same number crest and crest. So they are all constructive interference. So here you will get maximum light, here you get maximum light, here you get maximum light, here you get maximum light. In between you should get minimum light, where there is 2.5 lambda difference, 1.5 lambda difference, half lambda difference somewhere here. Half lambda difference here, 1.5 lambda difference here, 2.5 lambda. That means in an angle of 190 degree in 1/4 of the circle, we receive maximum twice, thrice actually. You leave this one. We will count this later. So once maximum, second time maximum, third time maximum. 4, 5, 6, 7, 8, 9, 10, 11. Now we will count it as 12. Last time when I started, I left it, right? This is 0. 1, 2, 3, 4, 5, 6, 7, 8, 9 here. 10, 11, 12. So 12 maximas you will get. That is the one question here. 12 maximas you will get, 12 times bright lines you will get, bright light you will get when you, as you move, either like this or like this anyway, and 12 minimas, 12 minimum light. Now their question is, what is the angular separation for each maxima? That means this maximum light and this maximum light, how much angle they create here. Divide this 90 degree into 3 parts, because when you cross by 90 degrees you get 3 times the maximum light. So when you divide the 90 degree into 3 parts, you get 60 degree, which is pi by 3, right? Uh, yeah, pi by 3, yes. So pi by 3 and 12 is the answer. Where is the question? Or 1 minute, pi by 3 it should be. Here it is, so you should get 30, 30, 30 and 12. So you should correct it as pi by 3. It is not pi by 6. It should be pi by 3. Right, 12 and pi by 3 is the angular separation. Or you could have done no, not pi by 6, correct. It is pi by 6, 30 degree, right? 12 and pi by 6 are the correct answers. And suppose you divide 12 maximas in between into 360 degrees. It is 30 degree, it is pi by 6, it is the correct answer, fourth one. Hope you have followed it, right? If you want, you can get the video back and you can learn it. Or in short, if you want to say, no path difference here, there is a path difference of 3 lambda, because this is given as 3 lambda this distance. So this wave has to travel extra 3 lambda more. So that means this is the third bright fringe. That means third time when the crest falls on crest. That means 2 times in between must have fallen somewhere here. This distance minus this distance must be 2 lambda. Here this distance difference is 1 lambda. So you should get 3 times maximum intensity in between a quarter of circle. So 3 times, 3 times, 3 times, 3 times, 12, and each separated by 30 degrees. So answer is this one. So this is how we can understand interference. And now from here onwards, we will go to again a video classroom, where we have to find out the distance between 2 bright lines and dark lines, everything. So that is again, but that needs this basic idea. Once we go there, then we will get mathematical equations which explains everything. So with that, I'll conclude this class. Thanks for watching, and keep learning all those things, so that it becomes easier when you come to the college. Don't know when it is so, but still you can have some stuff inside the brain and you can enter the college. It becomes easier in the next coming days. Hope you will do that. Keep your health properly, and take care of your health, and all the best. Thank you for watching. Thank you.